Great. Okay. Thank you so much, Steph. I really do appreciate that intro and notifying everyone. So yeah, I will be sending out all of the slides from not only this training, but the past three trainings as a PDF so that you can have not only the resources that we also link to, but you can review the material of the slides. Note that we have tried to as much as possible, sort of work in line with public sources so that you can actually go back to other places and read through a lot of these examples and tips again. And hopefully this will be helpful in ensuring that, this repeated learning, that you'll make sure that this is enshrined in your mind, a lot of these basic and fundamental principles. Okay, so let me speak up a little bit. Yeah, as another note, if you do have a question at any point, feel free to raise your hand. I'll try and keep my eye on the participants tab. You can also use the chat function. That'll probably be a little bit easier to type your question. You can send it to everyone, or you can send it directly to Steph, and she can relay the question to me. If you prefer to remain anonymous, that's entirely understandable, right? And let's see, perfect, it's working. I'm always happy as the first slide goes. So today we are going to be going, this is the last of three trainings, so hopefully you recall, if you were here in the last 2 weeks, we covered basic statistics and fundamental principles, as well as going through a lot of the data collection that ensures that these statistical techniques actually do have validity. So now we're going to actually try and cap this off to explore a little bit more advanced techniques and talk about what place the data science pipeline and machine learning could have when we're trying to talk about a business. And we're going to try and unpack a lot of these terms and go through as you know, a data scientist, if you're looking to hire somebody, what you can sort of expect their process to be and their method to be, to keep in mind how it fits in with the other segments of your business. So hopefully this will be valuable. As one note, we were supposed to have another additional speaker here with me today, so you didn't only have to hear me talk. Unfortunately, they canceled sort of last minute here. So we won't be here till 1:30, hopefully. I will not talk for that long, I promise. But we will try to include as much information as they would have provided. I did take a couple notes from what they sent me, and hopefully it'll still be valuable. So we'll aim for about that 45-minute mark and up to an hour, depending on how much material we get through, as well as some time for questions. So yeah, today we're going through machine learning terminology. We're going to talk some about the applications and where you can see this pretty often. And then we're going to go into the data science pipeline and sort of these 7 steps that are really valuable and things to think about in the steps as something to look out for and be able to converse with the data science about. And then lastly, we're going to talk a little bit about the limitations of data, about the ethics around using machine learning, and what you should really be careful of when trying to deploy these types of models. And then, like every time, I do just want to mention that this is all pretty difficult stuff, and it's okay not to have your head fully wrapped around it within, just an hour of our time here today. Be constantly learning. We do have a resources slide at the end of this. Hopefully, you will take advantage of some of those resources and go through a couple of these, entirely free online courses or articles that you can really use to reaffirm what knowledge you gain here or that you already have in the past. So start small, make progress slowly. A lot of this does involve using some sort of code, right, to implement any of these models. You're not only going to need domain knowledge within statistics, but about your business, about the environment that you're working in, and then about the computer science required to implement these models and code them up. So I like this quote. I guess to a lot of people, and I think to myself too, when I was initially starting to learn about machine learning, it was a little bit difficult to understand, what exactly is going on? What is the intuitive explanation behind what we're doing, what we're going to go through, and how we're actually applying this? So I wanted to bring in this quote, and I'll read it. You'll find it difficult to describe your mother's face accurately enough for your friend to recognize her in a supermarket. But if you show him a few of her photos, he will immediately spot the telltale traits he needs. As they say, a picture, an example, is worth 1,000 words. This is what we want our technology to emulate. Unable to define certain objects or concepts with adequate accuracy, we want to convey them to the machine by way of examples. And so this is really important. This is a really good book. It's fairly readable as far as these types of books go. But you should keep this idea in mind that when we're talking about machine learning, what we're really talking about is learning by example, right? We're giving in some data, and the algorithm that we're going to be using, depending on what algorithm that we're using, is going to create rules, create categories, create relationships by itself, by what we're learning. And this is sort of similar. It's meant to emulate how we learn ourselves. We see certain animals, right? We start seeing cats everywhere. And as we see more and more cats from different angles, we're able to categorize them better and better. And so that's I think a really helpful, intuitive way to look at this is by looking at the examples of data that we have, by using historical data that we've already collected, that we can start to identify trends and patterns and associations and look ahead, so that when we encounter an unknown example, something that we haven't ever seen, we'll hopefully have some indication of how we can categorize this, or what we can predict a certain value of what something will be at a different point in time. Or we can identify the similarity. How close is this situation or this person to other people that we've seen in the sample that we've been working with? Okay, so hopefully this is a good starting place, and let's unpack this a little bit more. I think it's really helpful, because over the last 2 weeks, right, we talked a lot about data collection and statistical concepts that you should really be remembering, right? So we talked about the central limit there, and we talked about the importance of sampling, how we're able to make inferences about a population from the data that we're collecting, about being wary of where bias and mistakes can enter within the sample. And then we talked about surveying and in the correct ways that we can actually bring in data. And so we're going to move away a bit from these sort of classic statistical methods, to talk a little bit more about how modern organizations are using data, are using, sort of statistical methods and learning to produce predictions, to produce classifications and associations that might help inform our business decisions. Now, starting this, I do want to provide a little bit of a disclaimer, and we'll talk more about this at our end, is that machine learning always isn't necessary for, I think, a lot of problems that we're faced with. It does seem that a lot of organizations I've been with, we sort of adopt this tech-first approach, but we really want to start with focusing on the business problem that we have, right? So like last time, we reviewed a lot of these summary statistics and surveys and data collection. They're doable frequently with the knowledge that you have, right? So employing a customer feedback survey is always good practice. Holding focus groups and analyzing basic survey questions, keeping track of KPIs, of key metrics that aren't difficult to calculate necessarily, are often the best place to start, right? When we're thinking about machine learning or statistics, the general starting point should be with the simplest model possible. And then we're going to move on to the more complex. Some very complex models that we could spend quite a lot of time implementing may only offer, a few percentage points better in terms of sort of accuracy, depending on what we're measuring that by in our specific context. So that's really important to keep in mind, okay? So we're going to go and move on to actual what this is. So as we mentioned, when we're talking about machine learning, we're really talking about autonomous learning. And let me write this down. Hopefully everyone can see the text. Yes, good. Okay. We're not providing rules. We're not providing, strict distinctions. We're not providing already set categories. All we're doing is providing teaching data. We're providing the real world examples of what we've already seen teaching examples. So this might come from a lot of historical data. So we might take a sales data set that we've collected over the past, 5 or 10 years that lists not only the customer, but what they bought, how much it costed, whether they used, how much it cost, whether they used a coupon, how much time they spent in the store, what other items they bought with it, what were some of the demographics that they actually, the demographics of that customer. And so collecting all of this data, we haven't collected it generally with the explicit intention of doing machine learning on it. So we're using a lot of this historical data, and we're going to talk a little bit more about the dangers of using data that wasn't necessarily developed with this specific purpose in mind. But really, all you think about when we talk about machine learning is using just algorithms to detect patterns, right? So algorithms, and these are just like equations, you know, it's nothing crazy, algorithms, if I can spell. um, we're just talking about functions that give, you know, from a quantifiable number of inputs, from information, from pieces of data that we have, what output can we get from that? And that output can be a couple different things, right? So we're going to talk about what types of outputs we can actually sort of calculate and measure through machine learning models in a second, but I'll try and finish writing this down. To discern patterns and provide outputs. And so we're going to go through some of the terminology and examples of machine learning. So if we sort of imagine like the CSV file that we probably have a lot of our data in, we probably have ID and we probably have purchase and amount and coupon and sale. And this is all we're talking about when we're talking about feeding and training data, when we're talking about feeding examples. A lot of times it's just going to be like a straightforward Excel sheet, and we can think about, we're trying to use a distinct number of features. ID, right? That's not going to give us a lot. But we're going to be using a number of features to predict a single feature. So here we're going to be using purchase amount and the coupon to predict whether there was a sale or not. I mean, and excuse me, let me handle a notification on my computer. There we go. And so this is important when we think about purchase or amount, we're thinking about features, right? So these are certain variables that we think have some predictive power or that can inform our understanding of what is actually going to happen, of how we collect the output that we're actually trying to get. Each row then would be an example, right? So we have one, we have, oh, I don't know, coat for 20, and we have yes, and we have yes. Okay, so each row is an example, and what we think is that using this data of these sort of features of variables that may contribute to a purchase, we can actually predict one variable right here, right? So this is going to be our output variable. And so all of this, building on this requires an understanding of the entire process, I think, because when we think about what features we're actually going to include in a model, what we think might have some predictive power will have an effect on what type of model we end up choosing. Remember, when I'm saying model, I'm saying an algorithm, right? This is an equation that sort of sorts what values we have for all of these features into a yes or a no, or into a category, a grouping, or a similarity score, right? So the columns are our features. The sales variable, right? What we're trying to predict a lot of times is going to be called a label. So you're going to hear this a lot when we're talking about machine learning is labeled data. And this is really important to keep in mind that when we think about labeled data, we just think that we know what our output is. We know what we want to predict, and we have an answer for each of those. And so let's actually go, let's talk about this one, and then we'll go back to the applications. I think this might be a little bit better order to go through it. I have just 3 categories here. People define it differently, right? And data science it's still a rapidly growing field, and so categories are always emerging. These are, I think, the 3 general categories that I think are really simple to understand and bring some of the largest sort of differences that we can keep in our mind and explain pretty simply, right? So we have an algorithm, we have a model, just an equation, and these algorithms generally can be used on repeated data sets. So this is, I think, a defining feature when we're talking about this, is the way that we go about learning that same way can be used on multiple different data sets and work out pretty well. And so we're seeing quite a lot of examples from the past, and we're developing this model. We're using it to assign weights or to assign some sort of relationship between certain variables. And we can use this old data to predict what comes forward. And so this is what we think of as learning sort of in our own minds, and this is what we're trying to emulate, right? The algorithm is actually creating these rules, these distinctions, these relationships on its own. And it can also not be developing rules, right? Depending on the relationship. So machine learning is autonomously adjusting to how it responds when it receives new data. And this is happening through different types of algorithms. And it's just computer code right here. And so what type of algorithm that we're actually going to use when we think about developing or implementing machine learning into our business depends on a couple things, right? Not only the technical expertise, but we're talking about the outputs, and we're talking about what type of data set that we actually have, that what type of data have we collected, what type of data or what type of features do we have, right? The columns. And then we also have what we're trying to predict. And so these things impact what type of model we're choosing. And I think the most basic one, the one that we've even talked about a little bit in the past, is focused around supervised learning. So supervised learning, essentially, when we talked about regression last time, right, we were talking about drawing a best fit line. This is really similar, right? We're able to actually give in certain data that we know an answer to. So we know if a sale was made or if it wasn't made. We know what people like. So we understand that what we can predict is that they've enjoyed this movie, so they might enjoy another movie. We're trying to classify those in examples. This is going to be used in image recognition too, right? So we can label a picture as a dog or a cat, and then we can give it to a machine algorithm, and we can allow it to actually try to come to a similar conclusion using this labeled data. We'll give it a set of training data of all pictures of cats or dogs with the labels included. And this is really important, right? So this is when we talk about this notion of supervised learning. It's an idea that we have labeled data, that we actually know the outcome that we're going to try to predict in the future. And so this is, again, an importance on actually in the terms of data collection. And we're going to talk about this whole pipeline. That data collection is a really important part of when we're choosing a machine learning algorithm, is that if we have labeled data, we can use different types of machine learning that are often a little bit easier and more straightforward to implement than if we don't understand if a sale was made or not. So we're talking about prediction, right? We're talking about, are we predicting sort of a stock value maybe? We're predicting a value of certain things. We're trying to look into the future and say, okay, what value will this have at any point? Similarly, we're talking about regression, right? And we'll go into a little bit more behind the math of regression, but trying to draw that trend line of where values seem to be going. And then we have classification, right? So we might be just trying to predict a yes or no. Will a sale be made or not? Will my favorite sports team win or lose? Or we can talk about even more categories, right? So when we're trying to just, a lot of you probably have phones that you can type in 1, 2, or 3, or write in 1, 2, or 3, and your computer will actually recognize this as a 1, 2, and a 3 as numerals and can translate that into typed text, right? And so this is actually using machine learning to categorize these types of strokes, of pen strokes, that based on what it's seen, to classify it within a certain category. So yeah, we can have 1 or 2 categories, but we can have quite a lot more too. So I think this is a pretty helpful, straightforward explanation. Moving away from that though, we don't always have labeled data, right? I think one of the things we'll talk about in a moment here is just our limitations of data. But it's really important to know that when it's too expensive to go back and label your data. So I think a good example of this is sort of in the medical imaging community. So you might have tens of thousands of pictures that you think show a tumor or not, right? So MRI scans. And it's really difficult for even experts to go through all of that data and determine yes or no, right? It's very time intensive, and it's very knowledge intensive too. So categorizing, labeling all of this data might not make feasible sense at wherever you are in your business. And so what they can do is actually label a very small part of that data set and allow the algorithm to build off that. So that's kind of right in the middle here between supervised and what's known as unsupervised learning, is semi-supervised, is that we can use a little bit of labeled data to sort of start off our equation in the right direction, and then it'll learn from that as it goes on. And so I think that's a good example, right? When you have a lot of data, labeling it all might not be feasible. So then we can talk about unsupervised learning, which is when you hear about, neural nets or these really sort of advanced terms. This is what we're talking about, is detecting associations within data. So a really simple example of this is actually in Netflix recommendation system, where we're trying to determine the associations between what people like and what people don't like. So we think about sort of similarities between consumers, right? I might have very similar watching tastes in enjoying, Community and 30 Walk. Right? So I enjoy comedy shows, and other people who are very similar to me might also enjoy comedy shows. And as we develop these associations, we're able to group people into clusters by their taste, by what they've watched and what they've rated. And this can actually generate really insightful predictions based on, okay, all of these people have sort of liked these very similar things. It's very likely that this person will also enjoy it. And it seems really straightforward, right? The math behind it is pretty complex, and we won't even go close to it. So I think that's hopefully pretty helpful, right? And this is an important part, that when we're talking about recommendations, we're talking about clustering, we're talking about associations, right? So we're not explaining why just because I liked Community, I might like, I don't know, a different show, You, maybe. We don't exactly understand the relationship between what's going on, between why this set of people are grouped together. But we can understand that they're associated with each other, right? So this isn't causation. We're unable to establish causation through this type of learning. And even in supervised learning, in most machine learning, we're not trying to understand causation. We're not trying to pinpoint what exactly influences decisions or outcomes, and the magnitude of how much, I watched one show influences my ability to like a different show than one other. So that's really important to think, is that we're just establishing patterns and associations. We're not showing why something actually exists, right? Some of our input features might be better at predicting outcomes than others, but the magnitude of that relationship always isn't necessarily significant. Yes, Ozan, yeah, the recording and slides will be made available after the meeting. Okay. So consider that ML models are used for largely predictions and for making decisions, not necessarily insight or causal effects. So YouTube has this, right, in its recommendation system. It'll go through what I've watched previously, and it'll make a decision. The website will make a decision based on what I've watched and how much I liked it, and show me a video that I'm also likely to watch and enjoy. Now, for YouTube, I get recommended some weird videos, so I don't know how well that works, but occasionally I will click on one, and so it is pretty interesting that you'll see videos that maybe have been uploaded a long time ago, because we can't really explain, maybe why these videos are showing up or why it's recommending it to us, but other people maybe have watched these videos and either liked them or rated them highly or shared them to other people, right? Indicating some measure of satisfaction that it's taking into account when determining what to do next. And then lastly, we have reinforcement learning. This is not my point of expertise, so I really won't talk about this at all in this lecture. Basically, what this is talking about is when you think about a machine learning how to play a video game, right? You're setting it inside an environment, and you're giving it a reward when it does a thing right. So sort of like, I don't know, if you think about a rat in a maze, right? If it reaches the end of the maze, it could get a treat. And it's sort of learning how to do that based on the feedback that it gets when it does something well. And it can just keep trying entirely random things. And you can actually Google a couple of really interesting videos of sort of these types of algorithms playing video games, where it'll start out initially just doing random things, moving all over. And then eventually it's learning, because it's rewarded by developers, that, okay, this is what I'm supposed to be doing. It's supposed to be getting as many points as possible. And so it's learning by itself what actions it should take. Okay. And it's already 12:27. Yikes. Okay, so I do want to talk a little bit about sort of visually explore what these mean. So we're going to just draw sort of a bunch of points, if I can draw points. And we're going to generally make an association. This is just an X and Y plot that we've sort of seen. And when we talk about regression, right, linear regression is really the simplest model of prediction, where we're just drawing this line of best fit, right? We're trying to establish a trend line that goes through all of these points. And what we're doing is we're trying to minimize the distance between the line and between the points off the line. So we're trying to make sure that the line best fits all of these points. And then when we get a new point, or when we get a new, we're trying to establish what will happen when we make 10 sales, we can go over and we can say, well, this line extends all the way up here, and then we can check to see what its result is. This is really simple, right? So there can only be two, like maybe how long they spend in the store, and then we can say how much they spend. How spending. This is only two variables, but think that this can happen in multiple dimensions, right? You can use more and more variables. Now that gets harder to visualize, right? I can't draw that. But this is how it essentially works, is it's just drawing a line. Similarly, there are other types of algorithms that work sort of like this on a basis where, the line, it might not be linear, it could be a logistic regression. And this is what we're trying to do when we're trying to do yes or no values. So what it says is essentially there's a concept of whether a team will win or lose a game. And the algorithm, oh, I'm sorry, I'm getting an internet connection unstable warning every time. So I'll slow down a little bit in case my voice is blurred. The algorithm will determine the optimal point, the barrier, where it should start classifying things as yes or start classifying things as no. So we might have a bunch of, if you can imagine another graph where here's a 1, here's a 1 is yes, and 0 would be no. And we have a bunch of points down here, and then we have a bunch of points up here. And sort of what this equation would look like if we plotted it was right here. And we could say that, okay, well, if the probability of some team winning is above 0.6 calculated by the various metrics, then we would predict a win. That's pretty simplified. I'm sorry, I'm speeding up a little bit now. But there are a couple other ways that we can do this too, even more complex algorithms that allow us to group certain variables together and predict categories by sort of the space in between points. We can also develop algorithms that divide points into multiple categories. So we can draw almost squiggly lines. The algorithm can come up with to group certain points into specific classifications, okay? So these are supervised models, right? So these are ideas that we have labeled data, that we know what the outcome is, and we're trying to predict that outcome again. So if we had this line right here that divided in between, yeses and nos, and we got a certain point that they were in a store for X number of hours or something, and we decided that a point was plotted right here, we would put this on the no. Okay, so it's just trying to create divided lines. That's all this is doing. It just uses a lot of, slightly complex math to get to that point. And so we can also talk, then lastly, we models, which is just clustering, right? We're grouping points together, basically in common, that we can hopefully predict outcomes for better. So we'll move on. We'll talk about decision trees just quickly. This is, I think everyone sort of has this idea in their head of we start with, we're talking about sales, right? So we can say, how long did somebody spend in the store? So time, spent. And we can say, if it's greater than 5 hours, then we'll ask, did they have a coupon? And if they had a coupon, then we can say, yes, they did. And then we'll say that this landed in a sale. Yes, sale. And if they didn't have a coupon, then no, then this would not end in a sale. And here, if they spent in less than 5 hours, if they had a coupon, right? And so this will just go on and on until we get back to yes or no sale. And this is pretty straightforward. It's pretty easy to interpret, hopefully, is that we're trying to, an algorithm is defining boundaries of what best to split on. So what attribute actually creates the most predictive outcome that allows us to look at, that allows us to predict whether a sale will or will not happen based on how valuable each attribute is. There are a ton of different mathematical ways to sort of show that, to say, what attributes will we use to split up groups. So maybe we don't start with time spent, maybe using a coupon is a better indicator, but we won't get into much of that just because of time. Really, decision trees are relatively simple to implement. This is an advantage of them. They're easy to interpret and visualize as well, which can be really important depending on what type of business you're in. And they can handle both numerical and categorical data, right? So this is really helpful. And we can also talk about multi-output. So we might not be talking about yes or no sale, but we might be talking about a low value customer, a medium value customer, and a high value customer, or whether a customer is going to leave because they've stopped engaging with our product after a couple months. Okay. So we'll move on quickly again from there. We'll talk about text analysis a little bit too, which I think is important. And so we can talk about sentiment, which is really common. What we'd really like to know, good or bad. Is a review good or bad? Or we'd like to know sort of the relative importance. So we'd like to understand, what is a document about? And we're able to calculate this essentially by determining the relative frequency of words within a document and relative to other documents like it. We can also determine similarity between two documents as well. So this is really helpful in, again with the spelling. So this is really helpful, I think, in market research right now. So for instance, I've been doing market research for an organization about a certain type of software, and there are plenty of websites that host reviews about different softwares. And so we can pull those reviews, and I think we have about 80,000 reviews about certain software types. Now, we can't possibly read them all, right? But we can catalog them into, yes, this was a positive review, or this was a negative review. We can look at the number of features that were mentioned, conditional on it being a positive or negative review, to better to determine, should we have these features in our software when we're launching, or can we ignore them? What are some of the common challenges that are repeatedly coming up in different types of software? What this sort of works on is if you have a paragraph of text, right? And we're not even going to write it, but we're going to split it up into words. This is called tokenizing. And so we're going to just keep splitting up into words, and then we're going to get the base of these words. So similarity is really just similar, right? And this allows us to count the relative frequency of each word. And that we have algorithms that can actually do this automatically, right? So it's not like we're sitting down and cutting each word up into one little piece, but we can actually count and create frequency distributions based on how important words might be. And there are more advanced measures to understand what types of words are being used. And so this can be really helpful, right? Obviously, especially if you're in text analysis or doing some work on market research, we can better understand what's going on through this sort of unstructured data that might not be just strictly numerical, that doesn't seem easy to categorize. But we can understand, and we can break it down by, we could break down these positions by reviews, by whether a CEO or an employee was using this software. And it can allow us to gain some sort of understanding of how people think about a product, right? You can also see that this is done frequently on Twitter data, on publicly available data, to analyze market launches, to understand, okay, what are people thinking about this software? Note that this gets more difficult when we're thinking about using symbols like emojis or happy faces. But this is actually, there's work being done to sort of catalog and recognize, okay, this is a happy face, it's a positive emotion. So long ago, scientists have actually come up with sort of big word banks and emoji banks that catalog good words and bad words that might indicate sentiment for other people to use. So we're going to move on to sort of our data science pipeline. And I think this is really going to be helpful when we're thinking about business, when we're thinking about hiring a data scientist or multiple people to work with data in our organization. I think generally we can sort of separate this into 7 steps that I think are pretty important. There are a bunch of variations on this, as always. So I can't say that there's any real official guidelines, but I want to go through a couple things that you should be thinking about for any data analysis projects that you might be doing to improve your business. So the first one is plan. And this might seem simple, but I do actually think this is really important, right? So machine learning is, right, it's adjusting how we respond to new data, right? And this is happening through algorithms. This is happening automatically. And it's important to note that the type of data that we're collecting about what business outcome that we're trying to predict is really important in determining the machine learning algorithm that we use. So we shouldn't be thinking about, okay, we shouldn't jump right ahead to what actually algorithm we want to implement, what are we focused on doing, how can we do this technically, but focus on the business outcome that you're trying to predict, right? So creating an analysis plan is really key, right? Understand the outcome that you're trying to predict, understand your goals, understand the decisions that you're going to make off this data. So in organizations that I've been at, we can come up with some complex model, but if no decisions are going to actually be made on that model, then it just sits around. It's also important to talk about just trust with your employees on this. So we had a model that made recommendations, but no one was really unsure of how, everyone was really unsure of how it worked. And it was confusing about, okay, how should I actually implement this into my decision-making process for staff that weren't sort of inclined to understand this motivation, right? So the question that you are trying to answer is very important, as well as how the level of data literacy, how people interpret the model is really important, right? So these are a couple key questions. You know, are you looking for a yes, no response? This type of question will influence the type of algorithm that you choose. Are you looking so that's a win or lose, a sales made or yes, right? These would be an example of a classification problem. Or we're trying to predict a value, right? We're trying to say how many sales will be made in November and December. We're trying to see, you know, how much of something rather than just a yes or no. And that's really important too, right? So keep these in mind. We have to focus on narrow questions, on specific quantifiable objects. Now, I actually think it's important to start with a general sort of outcome. So don't try and form a question that will be quantifiable and work for data scientists. Right, start with a business outcome, a particular thing that you're trying to measure. Start with a problem that your users are facing with your product, whether that's, you know, calculating churn rate or when people, you know, so when people will leave, or how your employees are interacting with improving certain applications, or trying to detect when your product is failing. This is really important, right? So just because it might not be quantifiable initially, a question can come out of that could actually be used, right? So it's helpful to having this point to set some time aside. I like to do it with all involved parties. So the person that would actually be using it within this project, as well as the employees that would be using the model and taking advice from it. This is really important too when we're talking about a new project. So I've had friends who would go into organizations and be asked to just collect and aggregate data to sort of support the plan that was already in place. And that can be a little bit frustrating for a data scientist because they might come back with data data with instructions that don't necessarily align with what the business is trying to achieve, with what the department and the staff are trying to come up with. And that's going to lead to tension, right? So don't just bring somebody into a company to validate what you're talking about. It's also important not to just look at random relationships. And I apologize for not writing all of these things down. So if you have somebody come in to try and find indiscriminately variables that might be of significance, you might find spurious correlations. We talked about seeing, the number of murders rise with the number of ice cream sales sold, right? That's not helpful. That's just a correlation. That's a coincidence, a way that we plotted two variables together. So it's important, as somebody who knows your industry, as a leader of a business, as an entrepreneur, right? You know the context that you're working in. You have to suggest certain variables that you might think have an effect on the outcome that you're trying to predict, right? Data science can't work in isolation apart from the context that you provide. And so this is really important to have a plan, is to have this overarching business plan that your data scientists can support, right? And then again, think about the changes that you can implement when planning, right? So what action will you take, with this information? Sure, right? I think temperature might affect how many people go to a retail store, but you can't do anything about the temperature. So understanding, how valuable of a predictor that is, or what effect this might have in your sales, maybe isn't that important. Right? Maybe you can focus on a different variable that you could affect, right, feasibly, like how long people are staying on a web page or what your click-through rates are. So this is really important. You also have to plan for what type of data you're going to collect, right? So the data collection we'll talk about here in a second here, but this is really important. And maybe you've already collected your data. You already have historical data that you're looking to apply a machine learning model on. But keep in mind that the algorithm is just learning from the data, right, that you're giving it. That's all it has. It has no contextual information that you have. It does not have as good of an understanding of outlying variables that you haven't given it. So this is really important because bad decisions might come from the bad data. And there's huge potential for for human bias here when we're thinking about what variables we're giving a machine and about where it finds correlation. Right? So pair the data and the statistical techniques with intuition and real world examples, right? Make sure you have some context here. So that way, when you do come back with a weird correlation or something that doesn't make sense, you can say, oh, I understand why it's getting there, but that's not right, right? You're shortening that error term a bit. So identify the problem that you have first, and then if machine learning is a suitable solution, not the other way around, okay? So we're going to move on to collection, and we might go until 1. So machine learning is and it needs to be a lot of data, and it generally, hopefully, it would be ideally clean data. Usually, I don't know really of a lot of people who collect data, of a lot of organizations who collect data with this specific purpose in mind, unless they're larger companies, right? So we have to talk about what our data covers, right? And I think a couple key things are important to keep in mind, right? So our data coverage is really key. So if we go back to that example of we're trying to predict sales all year round, well, if we don't have any data from November, that's not helpful, right? Similarly, if we're trying to predict our sales, we have no way to account for a situation like a global pandemic, right? Our model is just going to be wrong in these situations. So as much as possible, we want to make sure that the data set that we're using, that we're giving the machine to learn from, is as comprehensive as possible. And by that, I mean that it covers all of these possible scenarios. Now, that can't happen all the time, right? There are just some things that are unpredictable. But as best we can, we have to make sure that it involves every sort of variable and situation that we could feasibly get into. It might be difficult to do that, especially so if we're thinking about calculating how much a customer how likely they are to return an object. Well, if only 5% of your sales are returns, that's going to be an unbalanced data set, right? So we're trying to predict returns, but we have very few returns within our data set. And so that's going to make it more difficult. That's going to force our model to be less accurate. So a couple things to check when thinking about data collection is, does it cover all these scenarios, right? That's really key. And then we need to think about errors in our data itself. So was the data possibly entered wrong, right? We have to make sure that these sort of errors that could lead to confusion within our algorithm don't exist, or at least that we can identify and fix them, right? We also need to think about the types of data too. So text, is it numeric? Is it categorical? These are really important to determine what type of analyses types are actually feasible. Okay. Now there are ways to work around and different algorithms developed for different situations, but as you expand sort of what types of data you have, you're going to have to use more and more models, and that's going to increase the complexity of the analysis that you're trying to do. So we're going to talk about cleaning data too, which is insanely important as well, right? So we can talk about algorithms as much as we like, but if we're giving unclean data, this isn't going to be valuable to a machine learning model, right? I think sort of the cliche is that a data scientist spends like 80% of their time on data cleaning, on preparing the data to actually implement a machine learning model, right? The machine learning models nowadays can actually be implemented in just a couple lines of code. And with the deployment of cloud-based solutions, right? So Amazon Web Services, Google Cloud, IBM has something, I'm sure. When we're using these services, they can actually handle a lot of these models, and they even have pre-trained models. So some of these things might be a little bit easier, but it's preparing the data for use that you can actually make efficient and well-positioned observations from is really important. So there are really simple things that we can do, right? We can calculate the min values and the max values. If it's sales, there shouldn't be a negative sales, right? You could have a return feasibly, but you have to make sure that's actually what you're measuring. You should look at the correlations between data, right? So check if certain variables are proxies for data. And this is important, especially too, when we're talking about bias, right? Because we might be using a proxy for something that's a demographic variable of a protected group. And if you're in business, especially if you're in like legal or healthcare, you have to make sure to be able to explain and justify the model and the variables that you're using to ensure it doesn't interfere with any sort of regulation and how you make determinations around your business. It's going to sound simple, but also knowing the names of your variables. So I don't know if anybody's ever looked through census data, but a name of a variable could be BC1048, right? It's not descriptive. And even variables that seem to be descriptive might just not be. That's sort of an easy way to say it. But you need to ensure that actually your variables that you're using reflect what you're doing. You need to have sort of a data biography, which I think it's called, of where the data came from, who collected the data, how the data was collected, why the data was collected. Was it collected for some purpose that might bias the sort of sample that you're using, right? The name of the data, the column that you have, is not enough, right? So try and plot out and identify any current relationships just by really simple methods that we've talked about previously, like a bar graph or a scatter plot or a line chart that you might actually be able to use, right? This doesn't actually imply validity, even if we get it from a really great organization, right? Quite a lot of steps go into developing a robust data set, so you just want to be careful, especially when you're aggregating multiple data sets together. Okay. So we're also at this point in the process, if we have categorical data, right? So if we have race data, or if we have certain types of tagged data that we can use, we can create dummy variables, which is essentially all I'm bringing this in to show that we can take text data, certain types of categories that aren't numeric, and then transform it into numeric. So don't think that, it isn't possible to do it if you have certain categories of, subscriber or not subscriber. We can actually transform that into numeric data that you can use within your mathematical models, okay? And then lastly, what data scientists do is they split their data sets. So we'd like to understand the accuracy of our model. And what we're trying to do based on the data that we have, is we'll actually be able to split our data sets into a training set and a testing set. And so typically we'll take about 20% of that data that we've collected and put it aside. So when we're training the model, when we're giving it all of these observations, giving it all of these examples to learn from, we're going to keep this other portion of data aside. And this is going to allow us to see how well the model generalizes to other situations. So when we talk about the accuracy of a model, when we're trying to figure out the best model of a bunch of models that we've tried, we can use this testing set, this data that the model has not seen before, and see how well it actually predicts outcomes or classifies what we know the true outcomes to be. So before we're deploying a machine learning model, we actually have some sense of how well that it's working, okay? So that's really important. Then we're going to talk, so this is actually the training aspect of it, right? So this is, we are giving the computer, the algorithm, examples that are labeled with what you're trying to predict, okay? That's all that training the model means, is you're just giving it a bunch of data and allowing it to run and establish these relationships. So if you had loan data, right, you would have a bunch of variables about their credit score, about their demographics, about where they came from, about what they were applying for, about the amount of money that they were applying for. And you're saying who got a loan and who didn't get a loan. And then the model is going to go over and create an equation that allows you to appropriately classify these variables into a yes or a no, right? It's creating its own logic. And so we talked a little bit about what these algorithms look like. I entirely underestimated how long it would take to do that, so I apologize if it was quick, but there are a ton of awesome YouTube resources that you can go online that do such a good job of explaining this, right? But apart from this, right, when we're talking about training the model, just keep in mind that all this is doing is giving examples. Amazon and Google, I know, I'm not here to, support them or say that you should use their services, but they actually offer now pre-trained models. So you can go in and say you'd like to classify your text into a topic. They've gone already, created a machine learning model, and then trained it on millions of observations, giving it a ton of data, so that when you give it your own data, it requires less data, right? So if you don't have as big of a sample as you'd like, you can outsource sort of the data collection that they've already done, and that'll give you a head start on what you're trying to predict, right? And so this makes it a little bit easier because it doesn't take as much time to do it or as much data as you need. Right? I think an issue that might come up here is that you don't have enough labels for each class, right? So when we talk about returns, you only have a couple returns per million orders, right? And so that might be really difficult. And then we might have some issues with actually generalizing this model out to new data, right? There's a big concern here called overfitting. And you're going to hear this a lot if you're ever speaking with data scientists about how models work. But this is the idea that you're fitting the model too well. So if we go back to the training data, so if we go back sort of to this regression line, you can make curvy regression lines, essentially. And we could keep giving this model certain data points and changing the model until at every point, it actually hits every data point that you have and can predict successfully all of the data points within your training set. But if you get new data points within your training model, it's not going to generalize well, right? So this shows this shows the importance of training and a testing data set for one, but it also shows the danger of overfitting, of making a model really complex to the point that it fits all of these training data points, but doesn't generalize well to new examples. Additionally, in the training phase, what's important to keep in mind is that we're generally using multiple models. So we're not just going to predict, say, one. There's a lot of tuning that can go into a model. So we can change, how many data points are going into it. We can change how well we weigh errors within the model. We can change how many branches we would like on a decision tree. There are a ton of things that data scientists can do to sort of increase the accuracy of their model. But they're always concerned about making sure that they're not fitting the training data set too well, okay? So hopefully that's at least a brief explanation of what that is. We are coming up at 1, so of course feel free to go if you have the time. I have a couple more slides on evaluation, deployment, and monitoring, and then we're going to be talking about the limitations of data and bias and the role of ethics in machine learning. So feel free to hang along, and I'll try to be quick and speed it up. So at this point, we do need to talk about evaluation. So there are a ton of measures for accuracy. Now, every time I spell a word on it, I'm terrified that I'm going to spell it wrong. There are lots of different measures, and this was really model dependent too, right? So depending on what algorithm we're using, depending on what mathematical formula we're using to classify or predict or show associations, the level of how we calculate error is going to be different in all of these circumstances. I don't think it's too important to know the specifics about this. Generally, a data scientist will be able to provide and explain a few straightforward measures of accuracy, of sort of how much variation that this model covers, of how many actual predictions you got correct and how many you got wrong. And depending on your business outcomes, you might want to use different measures of accuracy. So if we're talking about self-driving cars, the cost of getting an observation wrong, right, of thinking that a red light is a green light, is the consequences are massive, right? So we might want to minimize the number of cases that we're getting wrong. Now, this might seem sort of straightforward, like obvious, so you always want to minimize the number of cases that you get wrong. But the way that we create the model might have different measures of accuracy, where we can maximize the number, we can maybe get even some more right in the absolute sense, while also classifying more wrong. This is sort of, if you want to know more about it, it's called a confusion matrix. And we're trying to classify, oops, again with the spelling. We're trying to classify what the relationship is between getting things right and getting things wrong, right? This is actually really interesting too. So depending on the business outcome, I had a friend working on an application where they wanted to send notifications based on a machine learning model to encourage users to play based on their playing history. So if somebody always logged on at 9 p.m. to play a game, they might send a push notification on their phone to say, hey, just a reminder for you to play the game. But it's not maybe enough to get them to click on the game and start playing, right? They might want to maximize how long they actually play the game. So to play, they're looking at if they're playing for 2 hours, not just if they logged on for 2 minutes and then logged off, okay? So that's really important to consider specifically what sort of outcome you're trying to track and predict, because that feedback that you give the machine learning model will change what types of variables that you're predicting. And additionally too, just using basic heuristics is really valuable. And these don't even have to be really statistical in any sense of the words, right? But we can understand the measure of a performance of a model, right? At the most basic sense, if a store has consistently high business in a certain month, we can sort of assume in the future that they'll have high business again. Is the investment in a machine learning model and all of this work enough to say, yeah, we want to know how much more business they'll have, right? I get that might seem really simplistic and sort of contrary to the information that we've talked about already. But if you don't have a background with this type of technology, and this might require a lot of work, it might be too much. And that using these basic heuristics will inform our decision making about how valuable this type of model would be, okay? So I think that's something important to keep in mind. This is where our guest has his real strengths in deployment and monitoring of your model. I don't have too much experience of this, so just a couple points here that I think are valuable. Deployment and monitoring are really important, and it generally takes more than one person, okay? So we have data scientists who are generally coming up with the model, right? So they're developing a model, but we can also have a data engineer that's working to deploy the model, and we'll have app developers to actually ensure that the latency of the model is working, so how long it takes to get a response. We need to think about, are people using this model in real time? Do they expect feedback? Or is it just as a sort of metric that you're looking at only monthly, right? So how quickly do you need these answers, right? If you're trying to approve a certain loan to being given out, or a paycheck to be advanced, how valuable, how quickly of that information do you need? And think about also constant retraining. So when we actually, if I can write, when we're actually deploying and monitoring a model, we're not just putting one model in and leaving it for the next 10 years and assuming that it's always going to be working, right? We're going to be using new data as we get it to constantly be retraining the model, to giving it more information. This is especially important if you think that the trends have changed, right? So if some shift in your environment is actually happening that might interfere with the accuracy of a model. And you should also think about the behaviors of your customers. So something that might happen that would, for instance, prevent people from going out to retail shopping or restaurants, that's going to interfere with how people act. And if you think that either of these two things have changed, then you really should reevaluate what type of model you're using and what type of data that you're giving it, okay? And then lastly, just monitoring the model. There are so many mistakes here at this point. I think you might actually remember a couple years ago, Microsoft released a chatbot on Twitter. And they just said, hey, everybody, talk to this chatbot and it'll eventually learn how to talk based on the input that you're giving it. Of course, internet people are not good people. And so after a few hours, this chatbot was just essentially using vulgar, racist, and sexist language because people were giving it that input data. So this is a failure, in monitoring, right? This is also a failure in common sense and expecting what the internet would do, right? But it's important to keep track of how well your model is performing and making sure that these outputs make consistent sense and that they're not becoming biased, okay? So monitor for clear changes in the behavior and the environment that you're working in. That's really important. We can also think sort of about if we looked at the improvement of a model over time. So you're going to have big jumps when you feed in your initial data, right? Because this is the first time that it's seen anything, and the accuracy is really going to increase quickly. But as you just feed in more and more data, it's not going to perform as dramatically. Sorry if my internet is cutting out again. I'm getting the unstable message. But you can just assume that the increase in your model as you go on will not be as much, okay? So that's the pipeline. It's 102. Just a couple important things. Think about where the data that you're working from, right? We might have missing data. This is going to affect our observations. There's a statistical term. You can impute data. Imputing data essentially just means you're making data up, but you're doing it statistically. So you might actually replace missing data with the mean, with the average of a certain variable, with the average sale price, okay? So there are ways around missing data, but ideally we won't have any missing data. We can also think about the limited coverage. If we don't have an image recognition, if we had a million pictures of giraffes all from the side, if we saw a picture of a giraffe's face up close to the camera, that's going to be really confusing for our machine learning model to figure out, right? So it's important to understand, again, the coverage, right, of making sure that you have all relevant scenarios planned out for. We can also talk about redundant data points too. So some data points won't be as predictive as others, and that this might actually interfere slightly with our predictive and sort of interpretation of the model. We should also talk about just human error you have to be aware of. People input data poorly a lot of times. It's not the most fun job. And so when you're doing it by hand, you have to ensure that human error is minimized as much as possible. Again, a lot of that can be sort of headed off by proper data exploratory analysis and cleaning in the initial phase, right? You really have to understand the data that you're working with when coming up with a machine learning model. So don't be surprised if this takes quite a long time, okay? And then lastly, I'm just talking about the labeling of the data, right? This is going to affect what type of algorithm we can actually use. There are resources. I know this is really time intensive. But I think Amazon has an initiative called Mechanical Turk, which essentially pays people maybe a cent to label a picture as a cat or a dog. And you can actually get labeled data that way. I don't know how exactly that works for businesses, but it might be something that to look into. It's kind of interesting. You can note that the training data set might not be representative of the end user as well. So when we're developing a machine learning model, there's a lot of papers writing about how the people programming machine learning are data scientists. They're not thinking about the person who's actually using this. They're not thinking about the end user in this mind. And so that can put a lot of people off when they're trying to use a product. So make sure to be incorporating sort of UX or UI designers when you're developing a UI model that might have some more input in how people would actually be using this model, taking advice and interacting with it. Right? So this is an incredibly important part of the work for data scientists, being able to clean data, document the process, and to take steps that are statistically sound for developing these machine learning models. So keep that in mind too, right? It's really important to be able to replicate these steps, especially if you're in a business or an industry where people might want to ask to see what you're doing. And then lastly, yes, Steph, I can do that. Sorry, I saw your message. I can't type. So supporting data use as a culture within your organization. So it's really important to understand the alignment between what needs to be done and what action you can take. You can build a solution, a technical solution, and your coworkers just might not want to use that, might not think that the numbers you're bringing, that the data you're bringing is really valuable. A lot of people sometimes don't like learning the new software, and they might not trust the algorithm. They don't know what is actually happening to come up with these sorts of numbers. And so this is important to keep in mind. This actually happens, we can talk about it in our criminal justice system. They now have, they've developed machine learning models that essentially calculate the risk of somebody violating parole. And judges can use this information based on all of these different heuristics to decide how much bail should be set. And so it's important to keep in mind about, okay, how are these numbers actually calculated? What is the data that's being used to develop these numbers, okay? So how is it integrated well within existing operational processes is a key question, right? This requires a ton of discussion too. I think not only on the developing the model side, but making sure that the product is actually helping the people that are solving the problem, right? So even though a number it encapsulates sort of a complex situation, how helpful is this, right? What action are you going to take from this model? So I'm going to ignore, I think, the rest of this. Think about the pipeline, think about the continuous monitoring and integration, about how you can be improving this over and over again. The data science in your organization, the scientist or the analyst or whoever's doing this type of work needs to be able to communicate on the business side about what is happening. This is, I think, really important and sort of underrated when we're talking about hiring. Somebody who's able to explain a complex model succinctly and well is going to be really valuable, because if you ever come under any heat about how you've calculated certain metrics, it's going to be really helpful when you can explain to your leadership about why this is valuable and about what advantage comes from understanding this. Standardizing your data, they should be able to comfortably talk about, any ethical risks or biases that could have arisen within the process of cleaning the data and using the machine learning model, and how well it can predict in the future. So this is really important, as well as implementation too, right? So whether you're creating an API that users can access, or a web form that people can be used that can have open to input information and instantly receive information. So it's important to have that sort of contextual connection between your data scientist and the business side of your organization, okay? So then we'll just go into, so quickly on regulations. Increasingly, we're seeing oversight over these types of models already under the American with Disabilities Act, under the civil rights legislation, under in Europe the GDPR, which is focused on the privacy of certain organizations. And I think California has some fairly strict regulations on user data too. Using your user data to develop predictive models, depending on what sort of variables that you're using, might be subject to legal scrutiny. So keep this in mind when you're trying to understand what models you can create and feasibly use, okay? it's important to think about interpretability of your models. We haven't talked about this much, but already just explaining it within this short time, that it can be difficult to explain the math behind these models. And so when you're trying to explain to a customer about why something was recommended to them, that can be really difficult to do, right? So I think there's stories about Target sending items for pregnancy to young women before they even knew that they were pregnant, right? That level of user data and knowledge about who you're trying to communicate with can come under some heat. And okay, they shouldn't have this data. Why are they using it to predict their business model, and then how they're sending these coupons and items to me? Okay, so be able to justify and explain the process that you're using. Be careful of any proxy variables that might stand in for demographics of protected groups. Okay, so that's really important. Bias is really important. We tend to think of these models as sort of being machines. They're not biased at all. They're working from some objective standpoint. That really isn't true. Okay. When we're constructing these models, we're bringing our own implicit biases to lend on this math, and a lot of times it can actually be sort of these social stereotypes can be embedded within these models. So when we're recommending what's popular might be pretty terrible things that your company doesn't want to be recommending, even if a lot of people are watching it. So be careful in those types of things when you're talking about recommendation systems. And then lastly, sorry for going over time again. These are a ton of resources. We'll be sending these out. I tried to pick as many resources that I thought were clear, that were accessible to a business audience without a lot of technical knowledge, that are really important. There's a ton of free resources out there that you can use to better understand data science and machine learning as a whole, as well as to learn yourself. That'll take some coding, that'll take some math, it'll take statistics, but it's a really valuable skill to learn. And even if you don't have the best understanding or can't implement one of these models yourself, understanding the pipeline of what's going to happen should be really important. So thank you all. I will send all of this in PDF format to Steph as quickly as possible. All of the decks will be available across the entire series, as well as all the videos. At some point, I think we'd like to return this summer to film shorter versions of this. So, me more concise would, I think, be pretty valuable and nice, as well as bring in some more specialists to talk and refer to more specific problems. So I do appreciate it. I'll be around for a couple minutes. If you have any questions, feel free to send a message in the chat. Otherwise, thank you all so much. I really do appreciate you listening. Yeah, appreciate it. Have a good day. Enjoy the weather. It's sunny outside.
Thanks again, Jacob, for hosting. This was a lot of fun. I know last time you mentioned the book, I think Naked Statistics. I picked that up along with like the Nate Silver book, and those two have been really entertaining. Is there anything like for the novice statistician, like books like that, popular books that could help me get a more of an intuitive sense of how to make this work in my context?
Yeah. So definitely great call. So The Signal and the Noise is the Nate Silver book. That's a fantastic book. I highly recommend. It's super readable, I think. Naked Statistics, I think, is a really readable book as well. I just ordered a book called Bayesian Statistics the Fun Way. And so that looks at sort of, for people who don't know, that's sort of talking about probability. I haven't read it yet, but I've heard really good things about it, that it should be, they explain it through, I think the subtitle is something to do with Legos and rubber ducks. So that might be something to look into. Yeah.
Cool. Thank you.
There are a lot of good online resources too. Khan Academy is generally pretty enjoyable. Yeah, Charles. So I haven't used any tools from H2O. I know they're one of the better websites. So the H2O AI is sort of a platform for deploying AI models and can be really helpful. I think I put in one of their links here that they can provide really good models. I haven't used their platform as well though. For time series data, it really depends on what you're trying to predict or classify. That can be really difficult. So the normal idea of splitting your data into training and testing sets, for instance, doesn't really apply, right? Because we're looking at trends across time. We're changing, they're autocorrelated, right? So just splitting the data might not really be helpful. It'll actually interfere with your estimates. So there's different methods for developing holdout sets when you're trying to test models. But it really depends on sort of the context of time series data that you're working with. So if you'd like, you can absolutely reach out to me through, oh, yeah, I'm sorry, Joni. Apologize for breaking up. Yeah, so I will add these to the links and send them on. Yeah. Yeah, I do apologize for my internet connection. Hopefully the recordings will be, you can understandable. And I just put the email in the chat too, if you have any further questions that I can talk about. And I think it's Charles Whelan. I don't remember the author of the Bayesian statistics book, but I'll post it in this sort of slide deck and send it to you. Okay, so thank you all much. I will hopefully I'll see you again soon at some point. Feel free to reach out to me if you have any questions, and hopefully we can get you connected with some resources that'll be valuable. Have a great day.